me just talk about the contents of today's presentation. Okay, Neerav Vyas, before starting the session, can you brief upon the future of IC engines as electric car is just knocking the market? It's just knocking. Well, I think you kind of pointed it out there, right? Yes, it is. I think the end goal is to go to electric, but there is going to be a lot, like all the companies, especially all the companies that make these cars, OEMs like GM, Hyundai, are still researching or are still spending money on researching ways to improve IC engines. And the reason why they are doing that is currently IC engine is one that could actually meet the market demand. So you need to be like, in terms of worrying, if you get to a point where you're able to get a replacement battery for your bike, just like you're able to fill petrol, I think that is the point where IC engines will stop to exist. Till that time, IC engines will always be there. As long as they are there, they need to be improved. That is my viewpoint on this topic. I hope that makes sense. All right, so let me talk about what we are going to be covering today. So we'll basically talk about why should we simulate IC engines, and I've kind of answered that question when I tried to answer Neerav's question. Then we'll talk about current design challenges and how to look inside an engine, right? Like how do we actually look at inside engine and how to figure out how performance improvements can be made. And then we'll talk about computational fluid dynamics. What is computational combustion? Because at the end of the day, CFD and computational combustion are currently the state-of-the-art tools that are being used to improve IC engine performance, period. So understanding what CFD means, understanding what computational combustion means is very, very important. Especially I see that Neerav and Darshil are interested in doing their masters, right? So you guys need to be quite aware of what CFD is and what computational combustion is. And this actually is very useful because even though you're studying CFD with respect to IC engines, no one is going to categorize you as an IC engine guy. They're going to categorize you as a CFD guy. And CFD is always going to be there as long there is flow problems involved, correct? And the techniques that you learn to solve flow through an IC engine is basically the same techniques that helps you simulate flow through a HVAC system, for example, or simulate flow through a gas turbine or through a combustor, right? So learning CFD and learning IC engines are completely two different things, okay? Then we'll talk about some challenges in setting up IC engine simulation. So this is where we get quite deep into IC engine simulation and setup. And what I would do is, at this point, depending upon, what you guys need, right? I can kind of condense the level or expand on technical points, as you tell me, okay? And this is where I need your input. But before I proceed, so Neerav, did you understand my answer? Do you have a follow-up question? Okay, perfect, cool. So why is IC engines required? Well, partly because, IC engines produce emissions and they're not that efficient, right? So why IC engine simulations are required then? Why is that a solution? Well, IC engines are a device that have been existing for a while, correct? Let me just get my microphone closer so that you guys can hear me. Like I said, IC engines are a device that have been existing for a while. So since it's been a while, there are a lot of engineers like you who have tried to optimize this system before and they have succeeded. Previously, this type of a success could be attributed to very simple calculations. A very simple example is, the thermal efficiency of an engine is proportional to the compression ratio, right? So I'm pretty sure you guys have all studied Otto cycle, where there's a formula called 1 minus 1 by R power gamma minus 1. You don't have to know this formula, but basically the idea is when your compression ratio increases, your thermal efficiency increases, correct? And in fact, the variable compression ratio technique is completely based on that simple formula. And I'm pretty sure you guys know that there is a new technology which is called as variable compression ratio, right? Though the concept is very, very easy, which can be derived on a piece of paper, it's been implemented only right now. Similarly, there are a lot of other technologies which have been implemented or still are being implemented, in the process of being implemented. So the idea is these type of analytical work can take us far, but it cannot take us really, really far. At some point, you need a better vision, right? You need to see inside an engine. And for that, there is experimental techniques. There are experimental techniques, but as I will show you, there are some bottlenecks to it. So that is why IC engine simulations are very much required, because that is basically giving you the extra set of eyes that you need to take a look at what is happening inside the combustion chamber. Because remember, only when you understand what is happening inside something, you can try to figure out what the problem is. If you don't know what's going on, then there's no way for you to identify the problem, which means there is no way for you to find a fix for the problem. I hope that makes sense. All right. So let's talk about how combustion takes place, right? So most of you have this particular 5-block view. I call this as a 5-block view because there are 5 components to it. So typically for combustion to take place successfully in your car or in your bike, you have these 5 elements that are interplaying with each other. The first element is your fuel, right? Your fuel is very, very important. And when I talk about fuel, I'm talking about the fuel system. So this can be your carburetor, or this can be your fuel injection system. Similarly, on the air side, what I'm talking about, say, the geometry or any other valves, the throttles that are involved in taking air from the ambient inside your engine. So this is block number 2. And finally, both of these 2 components react. When I say react, they interact basically to control the fuel and air mixture quality, right? So what do I mean by mixture quality? Well, is my air and fuel mixed very well? Is it mixed okayish, or is it not at all mixed? How do I quantify this? How do I put a number that can tell me that, okay, if my air fuel mixture variable is this much, it means everything is mixed perfectly, else it's not. How can I quantify it? Similarly, combustion. Finally, depending upon your type of engine, whether it's a spark ignited engine or a compression ignition based engine, your combustion event changes, right? And then finally, when combustion takes place, your fuel and air is going to result in products which you call as emissions, correct? So this is what I call as a simplified diagram. Now in the simplified diagram, if you are able to optimize even a single system, meaning, for example, let us say that you are able to optimize the process of creating fuel and mixture, that means you are taking a step forward towards optimizing an IC engine. I hope that makes sense. So for example, if you make the mixing process more efficient, then yes, you can get some advantages in reducing emissions and also gaining some performance improvements. But what does making the mixing process more efficient even mean? Can anyone answer that question? How can you make the mixing process more efficient? What are some of the technologies that are currently available? Can anyone answer that question, please? It's a very simple question, so I'm hoping for all of you to answer. ECU, electronic control unit. How does it make the mixing process more efficient, Nirav? Fuel injection, okay, that's good. Fuel injection definitely makes the mixing process more efficient because it atomizes, it helps in better atomization of the fuel. Harshit, more air and less fuel maybe? Not really, right? So we're talking about the mixture, right? So even if your fuel amounts or air amount changes, mixing is completely different. Nirav Vyas, the mapping in ECU which decides the intake time. Well, you need to understand that ECU is just a controller. It basically looks at your exhaust O2 and then tries to modify your fuel injection accordingly. But even then your mixing process can be inefficient. I'm just talking about what you can do to make the mixing process more efficient. Well, so this is where the concept of port design comes in, right? So if you're taking a gasoline engine, most likely a GDA engine or a direct injection engine, then these are being devised for something called as a tumble flow, right? I'll talk about what tumble means shortly, but that is a particular type of flow pattern that is beneficial, all right? And similarly, if you take a look at diesel engines, then you have something called as the helical port, which helps in generating more swirl, which is beneficial. How about increasing or decreasing the compression of the piston? That might have a benefit, but again, if you're talking about mixing, more than the compression of the piston bowl shape is more important. So that would be a valid answer, but not the compression alone will definitely affect the mixing process, but it is not going to be a deal breaker, say, such as using a flat piston versus using a re-entrant bowl, correct? So the piston bowl design or the combustion chamber design is very important. Yes, that helps in your mixing process. Similarly, combustion, right? If you're able to make the combustion more efficient, then things will be better. But that's the question, right? Whenever you're talking about making things efficient, you always need to engineer the problem. Meaning, see, for example, say that you are basically working with some type of a system, right? And you're trying to optimize it. All right. So the question is, when you're trying to optimize it, you need a performance metric. Say that you're designing a vehicle and you're trying to optimize your suspension system, right? You can tighten the springs and you can modify your dampers and you can change your camber, caster, toe in, toe out, all that stuff. But how would you measure the performance of the vehicle, right? There has to be a particular metric. What would that metric be? Well, how fast can I complete a particular lap, right? That is a metric. So there is the metric that you're looking for is the time, correct? Time to finish a particular race. But how do you put a metric for combustion efficiency? Can anyone answer that question? Neerav Vyas, what control this injection port? Neerav, maybe try to rephrase your question, maybe type in a longer answer. Harshit, compression ratio is a kinematic or kinematic quantity, right? Because it is a geometric parameter, right? It is just the ratio of volumes. How does that make your combustion more efficient? Like, when we're talking about efficiency, right? Isn't there something like 50% efficiency, 60% efficiency? How do you measure that? By measuring the brake power available. Oh. Yes, that is one way of doing it. But how do you measure combustion efficiency alone, right? So when we talk about brake power, there are other factors that are coming in as well. But how do you isolate the work that is being done only during the combustion? Well, you can do something called as an energy balance and then figure out what is the rate at which heat is being released inside the engine, correct? So for example, if this is theta, your crank angle, and if this is pressure, if you take a look at a diesel engine, then the pressure curve is going to look something like this. So this is what you call as a P theta diagram, right? You might have heard of it. Whenever people are designing an engine, this is something that they look at, because the area under this curve gives you the power output, and the rate at which the work is being done, the area under this curve basically gives you the power output of this engine, which is very, very important. And obviously you can get the torque as well because you have the RPM as well. Now, if you look at this P theta, basically what's happening is compression is taking place and then suddenly there is an increase in pressure because of combustion, correct? So on the same graph, maybe I'll use a different color and let's do a Y2 axis. So I'm just going to do a Y2 axis here. And I'm going to plot something called as HR, which stands for heat release. Maybe I'll use green color so that it makes it more distinguishable or discernible. So what's going to happen is initially you're doing your compression stroke, there's no heat release. So heat release is 0. And then just before, since this is a diesel engine, there is going to be an ignition delay, right? Suddenly there is going to be a heat release. It's called as a premixed heat release spike. And then there is a heat release profile. And then the heat release dies down. This is called as the heat release rate, HRR. The unit for heat release rate is joule per degree or joule per theta. What you can do is you can integrate this curve and calculate something called as IHR, which is called as the integrated heat release rate, which basically says what is the total amount of heat that is being generated just from the combustion process. Now, if you're measuring the brake power, like measuring the work done, then the frictional losses are all gone, right? You're taking into account the loss because of the friction. But what we are basically doing is we are forgetting the friction. We are forgetting the friction component, and we are basically saying, hey, I have this much amount of fuel. How am I combusting that efficiently? That for that integrated heat release rate is what is important. What I can then do is I can take the integrated heat release rate. I can divide that by the total energy that I have at my disposal. What is that? Well, I can take the mass of fuel that I have and I can multiply that by the lower heating value of the fuel. This would be called as the combustion efficiency. Excuse me. Right? So what the point that I'm trying to make is, as engineers who want to learn CFD, make sure that you first understand these fundamental parameters, because if you don't understand these fundamental parameters, then it's going to be very hard for you to come up with strategies that can help optimize the engine. All right. Finally, we have emissions, right? So emissions is basically something that is controlled by chemical reactions. And a sound understanding of chemical kinetics is required in order to, completely understand how your reactants, which is air and fuel, are converted to products. All right, so now the previous diagram, as I mentioned, it is a simplified diagram. So now let's kind of build upon it, add more layers to it to understand a much more detailed and complex picture of the IC engine combustion process. So first, you need to make sure that you have your fuel components, vaporization characteristics, and physical properties. Well, why is that important? You need to understand that your fuel, right? For example, say you go to your petrol bank today, it is made up of thousands of species. What do I mean by species? Well, that basically refers to hydrocarbons like octane, alkenes, alkynes, and benzenes, right? Aromatics. So your fuel is made up of all of these components. So it is very important for you to understand what your fuel is made up of, because each component will vaporize at its own rate, which is what you call as the distillation curve, right? So very similar to fractional distillation, right? You guys might have studied that concept. So basically, in fractional distillation, different hydrocarbons settle down at different heights because of differences in their vaporization characteristics. The same concept applies to your ordinary fuel as well, right? So remember that the fuel that you take from one petrol bank is always going to be different from the fuel in the neighboring petrol bank. Maybe you come there some other time, it's going to be different. It's always going to be different. So understanding this differences and designing your fuel injection system accordingly is very important. Okay, so Nirav Vyas, sir, CFD is only take care of combustion or also the exhaust system as well? It can do pretty much everything. So with computational fluid dynamics, you can design your intake system, which means if you have a turbocharged system, you can include that. Even before that, if you have exhaust gas recirculation, you can include that. You can simulate your IC engines, you can simulate the combustion, you can simulate the after treatment system all the way up to the tailpipe emissions. The problem is doing all of this is going to be very, very slow. All right. Then on the injection side, there are so many parameters you need to worry. Like what should be my injection pressure? Because that is a parameter that you need to set, right? What would you set it to be? What should be my nozzle configuration? Well, what do I mean by nozzle configuration? Say you have an injector and you have to take the injector. So for example, if this is your engine and say that this is your piston bowl, okay? And this right here is your piston. And I have my connecting rod here. Say that you have a fuel injector. Now, would the fuel injector be placed like this? Or would the fuel injector be placed like this? What is the right way? Can anyone answer this question? How do I decide which way I want my injector to be placed? Red one, why? Why is that? right? So these are very practical questions that you can think about. The answer to, so the fuel doesn't impinge on the wall. Well, in this case, don't you think the fuel is directly going to impinge because this is the shortest distance? Isn't the diagonal larger? Ivanshu, what do you think about that? Mayank Yadav, it distributes in a better way. How are you saying that? Green one, as it will cover more area with air inlet. Well, so that's the thing, right? So it is depends on a lot of factors, right? So if you think about it, the port design is something that you try to optimize it. So one of the things that people do is, if for direct injection engines, the thing is, before the spark starts, your fuel needs to vaporize. How will the fuel vaporize? Well, if you hit the wall directly, that's it. You forget the vaporization. It's all going to be liquid fuel, and your engine will basically give a very big, what's the word? It's going to generate a lot of smoke, right? It's going to generate a lot of smoke. So what should I do? Well, I need to reduce the impingement, which means when the spray comes in, I need to make sure that it does not impinge. That is not the only criteria, but my parcels get enough time to basically vaporize, right? Which means, yeah, you can see that this is the longest path. But what I can tell you is, in this type of configuration, so if you take the green injector, I can do a couple of things. What I can do is, I can design my intake port to be something like this. So my intake port and the fuel injector are aligned at the same angle. So if I measure this angle theta, my injector is also aligned along the same angle. So what will happen is, my fuel spray will come like this, and because of the piston shape, the air would force the spray parcels to take this path as much as possible. There is still going to be some impingement, but your bulk of your spray is going to take this path. And that is where the bowl design is very important. And this will help you in atomizing the spray, right? But so this is what you call as a tumble port. And this flow, right, this rotation, so you can see that the air, it has a rotation about the x-axis, where x is basically pointing normal to the screen. So when you're looking at the screen, x-axis is pointing towards you, right? So this is basically tumble. So tumble is basically flow above the x-axis or y-axis, assuming z-axis is basically the axis of the piston. All right. So this is, again, you can see that the concepts are quite simple, right? But so far, whenever I talk to someone, no one knows what tumble flow is, right? But now I hopefully can understand that it's a very simple design methodology that you can use, or flow methodology that you can use, to make sure that your fuel doesn't hit the wall directly. Harshit, can you explain again? Yeah, sure, no problem. So what I'm saying is, let me see if I have a video for this. Just a second. I'm just going to stop sharing my screen. I'm going to see if I have my simulation video for this. Else I'll just show it to you. Okay, so guys, can I see my screen? Harshit, are you able to see my screen? Okay, perfect. So Harshit, take a look at this video. So this is one of the simulations that I ran recently. So this is what you call as a tumble port. So you can see that the bowl has a particular shape. The bowl has a particular shape. And here, if I play this video, you can see that fuel comes in, but then it tries to rotate as much as possible. And then it vaporizes before combustion occurs. It's going to be quite easy to visualize in the next slide, where I'm showing the spray again, but in white color. So you can see that the spray comes in, right? So this right here is the axis of the spray, right? And you can see that my intake port, if I use a different color, my intake port kind of has the same angle, almost, not exactly, right? So what this is going to do is this is going to help you turn the flow like this. And that is called as tumble. So if I play the video again, you can see that it comes in like that, but there's some amount of rotation like this, and all of your spray is vaporized and combustion takes place. So that's your flame front propagating. So this is one of the simulations that we ran. And I hope Arshit, this kind of clears things up. So this is a tumble port. So in this case, the simulation that I ran, this is what you call as a tumble port, TP. Cool, all right. So let me just move back to this presentation again. All right. So the other thing when we talk about fuel is to talk about the fundamental physics, right? You need to try to understand how the fuel vaporizes, how the fuel breaks. Because if you understand that, then that will actually help you design your injection systems and also your combustion chamber, right? Because your fuel comes in, you know that the objective is to break it up efficiently and vaporize it as fast as possible in a controllable manner, in a repeatable manner, right? So you need to spend some time in understanding the fundamental fluid dynamics of these injected fuel droplets. And for that, people routinely study like fuel breakup, film formation. Film is basically when the fuel hits the wall, it's going to form a wall film, right? And then vaporization. When I talk about vaporization, there are so many factors. If you remember from the previous video that I showed, right? You saw that the spray was represented by really, really small parcels. How do those parcels vaporize? Well, what happens if there is a film formation? How does that vaporize, right? So there are so many things you need to think about, and only then you can understand the entire spray process comfortably so that you can design something to meet a particular limitation if you find one in the first place. How about the intake side? On the intake side, there are so many decisions you need to make. Do you have a EGR? EGR stands for exhaust gas recirculation. Do you have an EGR system? Is there an intercooler? Then how does the air or air plus EGR mixture come inside the engine? Is it a helical port? Is it a helical or swirl port? Is it a tumble port? What type of a port is it? That is why people look at something called as flow bench analysis, so that experimentally they can figure out what is the angular velocity of the fluid as it comes through the intake. People can actually measure that. Then you look at more additional concepts, because something like valve dynamics. Remember, your valve is what is allowing your air fuel mixture to come inside if it's a carbureted engine, or just allowing the air to come inside the engine if it is a direct injection or a direct injection engine. So in that case, the rate at which your valve opens and closes and the valve timings are crucial, because that will limit the amount of mass that gets trapped, and that will also determine the amount of blow-by. Blow-by would basically mean leakage, right? So for example, if the valve is closing too late, as the piston is moving up, some amount of charge can get pushed back through the intake. And if your intake has small leakages, you can have some fuel going out of that, right? So you need to understand that. Because if you're fixing any issue in that system, you are improving the overall engine efficiency. So what we are trying, our concept is very simple. Previously, we knew only 5 blocks that determined how engine combustion takes place. Now we already have 6, and we have a few more. The more the number of blocks, the more the areas where you can find for problems, and you can come up with some solution, right? You're increasing the probability of finding a solution by understanding more about the subject. All right. So then comes your fuel air mixture, and which is what you call as charge condition. And you quantify it. You quantify it as premixed, partially premixed, and non-premixed. An example of a premixed engine is your carburetor engine. An example for non-premixed engine is your diesel engine. And an example for partially premixed engine is your tumble direct injection engine, which we saw today, like a few minutes back. Why do we care what type of a mixture it is? Because it turns out, depending upon the mixture, the chemical kinetics, the chemical pathways that your system takes are going to be different. Meaning, A premixed combustion versus a non-premixed combustion would result in totally different emissions. Okay, it doesn't matter if even if your equivalence ratio is the same, even if your chamber conditions are the same, if it's premixed versus non-premixed, the combustion pathways, your reaction pathways are completely different. And this is called as fuel chemical kinetics. People spend a lot of time in understanding this. And you need to also try to quantify how the combustion takes place. So that is why heat release rate, combustion efficiency, temperature distribution, local equivalence ratio come. In addition to this, you can get some performance improvements by understanding wall heat transfer, right? Meaning how much cooling should I provide for my engine? If I provide excess cooling, then I'm unnecessarily wasting my combustion energy. If I provide less cooling, then I'm basically risking the chance of damaging my engine due to thermal damage, correct? So many considerations, and this is again at a grand scale of, compared to the previous diagram that we had, this is a much more detailed diagram which offers insight into what's happening inside the combustion chamber. But this is still a relatively simplified diagram. There are so many blocks. For example, your premix, non-premix, and partially premix can be further subdivided, based upon the amount of turbulence that you have, and things would get a little bit more mathematical and analytical at that point. But trying to get that entire picture is what an engineer should strive for as much as possible. So we talked about CFD, right? We have been talking about CFD for a while, but what about experimental data, right? Experiments are a great way. You don't have to worry about CFD, no mathematics, just look inside the engine and figure out what's going on. Well, a lot of advances have been made in that front as well. So, let's just take a look at a couple of those techniques and then look at some simulation data. But before that, I would like to answer a few questions. Any literature which we can refer for better understanding of these terms? Absolutely, Manshu. What you can do is, if you have never taken up an engine book, then you can first look at something called as Haywood Internal Combustion Engine Fundamentals, John B. Haywood. And typically, when you're trying to learn IC engines, you need to have a very good basics of fluid mechanics, thermal engineering, and combustion if possible. So for fluid mechanics, learning something like Frank M. White, or if you feel like the current textbook that you have is of good standard, you can keep following that. And for combustion, you can take up Introduction to Combustion by Stephen Turns. And for thermodynamics, Eunice Senegal or Shapiro, Greg Nellis, I think there are a few good books out there. Harshit, sir, can you please start with the fuel-air mixture again? Okay. So Harshit, here the point is, see, you have the fuel-air mixture, correct? The fuel and air mixture is there. How do you quantify this, right? Meaning, say that there are I give you three scenarios, and then you're looking at those scenarios and you have to say what type of a mixture it is, which means you need to quantify it. And that is what you call as charge condition. And there are three types. There's premixed type, partially premixed, and non-premixed. So premixed is, we'll be taking a look at an example. Premixed engine is where your injection takes place way early, so that there is a lot of time for vaporization to take place, and air and fuel have a lot of time to mix around, so that the air fuel mixture is uniform. Meaning, if this is your engine, at any point you will basically have the same amount of air and fuel mixture. And you can imagine this in a very simple way, Arshit. So say that you are in an air conditioned room, correct? Initially you just have hot air, correct? When initially you turn on the AC, the cold air is just now coming in, right? That is what you call as non-premixed. Your cold air is separate and your hot air is separate. Does it make sense, Harshit? Now think about the scenario where you wait for infinite time in the same cold room. Let us say there are no windows in the room. You wait for infinite time. What's going to happen? At everywhere, the temperature is going to be uniform, correct? right? That is what you would call as a premixed case. And partially premixed is something in between. I hope that makes sense. Let me know if you need more questions, if you have any more questions. All right. So let's take a look at the first experimental technique that I wanted to talk about, which is called as the Schlieren imaging or shadowgraph. Can you give me an example or this for the same? For which one are you talking about, Arshit? For premixed, it's going to be a carbureted engine. For non-premixed, it's going to be a diesel engine. And for partially premixed, it's going to be the tumble engine, which we looked at, which is basically this guy. The engine simulation that I showed you earlier, right? This guy is an example of partially premixed because the injection takes place just a few degrees before combustion takes place. Okay, perfect, cool. Does anyone have any questions? Again, guys, it would be really cool if you guys ask questions like Arshit. What about PFI? PFI is premixed. You're right. So PFI is a good example. GDI would be partially premixed depending upon the start of injection. So for example, the tumble port that I talked about, that I showed you, is actually GDI. Okay, all right. So, oh, sorry, I almost forgot this. So this is an experimental technique called as the shadowgraph or Schlieren imaging. Let me play this once, watch it, and then I'll explain what's going on. Okay, so I'll play it one more time. All right, so let's take a look at what's going on here. So you have something called as the time here. Look at the time. This is just ridiculous, like 5460 microseconds. So that's really, really fine time resolution, right? Because these processes take place very, very fast. So in 5460 microseconds, your fuel is vaporizing, right? So that's really, really fast. So a shadowgraph is a technique that helps you differentiate density values. So here, dark, anything that appears dark is having higher density. So dark is liquid, and anything that's light is going to be having a lower density. And in this case, that is going to be your air, right? So this is going to be your fuel, and that's going to be your air. And shadowgraph or a Schlieren imaging is a technique that helps you visualize this. Well, why do we do this? Well, in this process, you learn a lot of things. So if I pause this, you first learn something called as the vapor. You learn the spread angle. All right. So this is what you call as the spread angle, which directly affects the atomization capabilities. And then in this case, the reason why the fuel is dark all the way, right? So for example, here the fuel is all the way dark, but here it's light. That's because this is a vaporizing spray, meaning the ambient temperature is around 800 Kelvin or maybe higher than that. So let's say greater than 800 Kelvin. Guys, looks like one of you has your microphone on mute. Unmute. I'm just going to mute all once. Okay, perfect. All right, moving on here. Explain this guy again. So in this case, the ambient temperature, in the vaporizing case, the ambient temperature is greater than 800 Kelvin, whereas in the non-vaporizing case, it's maybe 350 Kelvin. So the reason why you do this type of studies is, well, you measure all the critical information that you want, and then you take this experimental data, and use it to validate your simulation results. This is called as the process of validation, because if your CFD simulations needs to be accurate, they need to capture all the trends that you see in real experiments, correct? That is why people take this type of data. If you're interested in this type of data, you need to refer to Sandia. So Sandia National Lab, N stands for National and L for Lab, is a research institute in the US. And they have a program called as the Engine Combustion Network. and part of which they're collecting, they are conducting and collecting really high quality data about sprays. And the reason why they're doing this is to support computational fluid dynamic research that is being done all over the world on this topic. Does that make sense to everyone? Any questions on this slide? Any questions on this slide, guys? Okay, I'm assuming there are no questions. If you have any questions, please do type it. Arshit, can we take non-vaporizing? All right, so Arshit, I'll let you type your question, all right? The second technique that you look at is basically a X-ray image, but it's called as an ultrafast synchrotron because of the time resolution. So here, what you're looking at, here is an injector, a fuel injector, and this is what you call as the nozzle of the injector. So this is nozzle number 1 and this is nozzle number 2. And this is really, really small. So the size of this nozzle is roughly 0.1 millimeters. Imagine how small that is, right? So in that small space, you're looking at the liquid fuel and you can see that this flow structure, for example, here the flow structure, this is the fuel, has this particular structure, whereas here, look at that, it has a completely different structure. All coming from the same, same injector and different nozzle, and it looks very, very symmetrical. The geometry looks very symmetrical, but you see these differences. That is because even if there's a small roughness difference between the two injectors, two nozzles, you can have a completely different flow pattern because the turbulence will be completely different. And why is this bad? Well, this means each and every time you're injecting, you're going to get a different flow pattern, which means the atomization process will not be 100% same during each injection event. This will result in a subtle variation in your performance. Now, if your injector has been machined very, very badly, you can have really bad outcomes also in terms of repeating the injection process and getting the subsequent combustion repeatable. So again, why people are doing this? Well, these are being done to make sure that the equipments that are being made, right? The injector, the fuel injector that is being made works correctly, right? For example, this right here is a needle. So this is what you call as a needle. The injector needle is supposed to move up and down because when it moves down, this surface is going to contact this surface and this surface is going to contact this surface. It needs to close perfectly. What happens if it doesn't, right? Well, then that is going to cause differences in injection again, right? And that is when you say that you have a broken injector, right? So people are doing this from an injector design point of view and also to aid combustion work or simulation work, because you can take these pictures and you can actually simulate this using CFD nowadays. With CFD has gone quite powerful from what most of you know where it was. It can do all these type of detailed analysis very, very accurately. And you can actually compare it with your experiments and figure out what's going on. All right. So we talked about sprays. How about combustion? Well, for combustion, we have a technique called a skimmingluminescence, where what we are doing is when combustion takes place, we are looking at certain species during the process of combustion, and we are basically highlighting them. So chemiluminescence, in the process of chemiluminescence, you pass a laser beam through the combustion chamber. Now this laser is going to absorb certain wavelengths, like certain radicals would absorb certain wavelengths, and in the process there would be chemiluminescence, meaning there would be light which is being captured. So here you're tracking OH radical, which is called as a hydroxyl radical, which is an important flame marker, meaning it helps you understand where the combustion is. And you can see that at different intervals in time, 1.5 milliseconds, 2 milliseconds, 7 milliseconds, you can see that you can gradually see the flame front propagation. Right? Note that this is not spherical, right? Your flame is not going in a spherical direction. So it's not spherical and it's not spreading equally in all directions. It is asymmetric and it is spreading in each direction at a different rate. And this is happening because of the level of turbulence that exists in the chamber, and the turbulence level is going to be different at different locations. That is why there is an asymmetry in the flame structure. Oh, Nitin, sorry. Thank you. Guys, when Nitin, did I just now get muted or have I been on mute for a while now? Thank you for pointing that out, Nitin. Really appreciate it. Last slide. Okay, just now. Perfect. So what I was saying here is this is chemiluminescence, where we are tracking a radical called hydroxyl radical, which is called as OH, hydroxyl radical, which you track. And when you track that and when you pass a laser beam through your engine, it has to be an optical engine, meaning the engine liner, there is an optical axis which helps you look inside the engine. In this case, it's actually a constant volume box, so it's not an engine. So it's just a rectangular box that's filled with fuel and air, and there's a spark plug. So the experiment is relatively easier to set up, and you're looking inside the engine. What I was saying here is, if you see the flame, it's not symmetrical at all. For example, if you draw this as your x-axis or y-axis, whatever, you can see that the flame has different spreading rate from the spark origin. In different directions, it spreads at a different rate. Right? This depends upon the amount of turbulence that exists outside of the flame front. The period between 0.5 milliseconds and 7 milliseconds, I would call that as the arcing phase. So you need to first provide enough energy so that there's arcing that takes place, right? And this is where the arcing is taking place, meaning there's a connection happening between the top and the bottom terminals, and that is what helps you ignite your mixture. This is also called as the glow arc phase, or the arc breakdown phase, actually, sorry. Okay, cool. So again, thank you, Nitin, for reminding me that I was on mute. What are the other devices? Well, the other devices are your regular temperature and pressure sensors. These give you information at a single point and as a function of time. So these are very useful as well. Now, as far as merits and demerits of experiments are concerned, I think we know it very well. It's high quality. The data is really high quality. Problem is it's low temporal resolution, meaning in certain scenarios, right? For example, if you're studying combustion in a box, then yes, you can get data quite accurately. But what if you're studying combustion in an actual engine, right? Well, you need really, really complex equipment to get high temporal resolution, meaning the data should be quite frequently taken. And the problem with that is you're eventually going to destroy that experiment, because if you're putting an optical axis, that's what you call as a transparent combustion chamber engine. The idea is the engine is eventually going to get damaged because you're having optical axis, which means you have a sapphire glass or something like that. The glass is going to break at some point. Setup is very complex. It's not easy to set up these experiments. In fact, people spend their entire PhD to just set up the experiments and maybe just take a little bit of data. And usually there are 2 or 3 PhD students that actually work on the setup. They take some experiments and then they graduate. And it's prone to errors, right? And that's why it takes as much time as a PhD, because you're going to make a lot of mistakes. You need to rectify your mistakes and fix the issues and move on, right? And finally, it's very, very costly, right? As you can imagine. With IC engine simulations, it's cost effective, meaning you just need computers which are very, very cheap nowadays. You can get very high temporal resolution. You can collect as much data as you want. The requirement or the problem that I see nowadays is you need to have highly skilled engineers. What I mean by that is, I'll show you some of the IC engine. I'll show you a simple IC engine setup right now. And you can see that setting it up the right way is actually complex. So you need to have a very good amount of application knowledge, and you need to have CFD and combustion expertise. So let's take a look at a live demo. And guys, while I'm opening up a couple of softwares, I just wanted to ask a question. How many of you are hearing us for the first time? Like, for how many of you this is your first workshop? If you can just reply back in the chat, that would be great. Harshit, thank you, Harshit. How about others? Neerav, Nitin, Darshil, Imanshu. Okay, all right. Good to know. Okay, so here, what I'm going to do is I'm just going to open up something called as a port fuel injection engine, right? So this is something that I set up. So I'll be showing it to you, and you can understand what's going on here. So this is a production engine, all right? Meaning, if you know someone at General Motors or Ford, and if you ask them about IC engine simulation, if you show them this model, they would recognize it. Meaning, this is very similar to a model that they are working on, right? It is so detailed. For example, if I show here, you can see that you can clearly see the spark plug. You can clearly see the valves. All the geometry is quite detailed. So this is a PFI engine, and you can see that that is the provision that we have for the injector. And here, if I hide the space, you can see the detailed flow path that is clearly being captured. And if I enable the edges, you can get some context. Right? Okay, so what does it take to perform an IC engine simulation on this model? First of all, how did I get this model? Well, if this is coming from SolidWorks, right? So when you're designing this engine, what we did is we have designed it in such a way that we are taking only the flow volume, right? So what do I mean by that? So for example, if I put it in front view like this, the actual engine, let us say this is an air-cooled engine. It's going to have fins, correct? It's going to have fins like this. And then for all the valves, what you'll basically have a valve block, and for your exhaust, there is going to be an outer like insulation layer, and your tailpipe, it would basically take you to the catalyst. Sorry, this is the intake side, so there's no catalyst. On the exhaust side, this would basically lead you to your tailpipe with a muffler or whatever, and then finally your tailpipe. But here what we're doing is we are not doing any of that. Since we're trying to simulate only the fluid inside the port, I'm just modeling only that. That is what you call as the wet volume. What engine is this? Well, this is a 4-stroke PFI, port fuel injected spark ignited engine. It's a made up engine. But it's made up, but when we made it quite accurately. Meaning, that is why I said this is a production quality engine, meaning that it has all the geometric features of a production engine that you might encounter in the future. Have you done meshing on the model? Well, this is not meshing. This is just the format is like that. So this is a stereolithographic model, STL file, which basically preserves the geometric feature in terms of triangles. So what I've done here is, first step is to break up the model. Let me display all the parts into boundaries. So I've taken all those triangles and I've grouped them into boundaries so that I can assign boundary conditions, because that is what you do in CFD. And then I also assign the initial condition accordingly. So the software that I'm using to do all of this is called as Converge Studio. So Converge is a very popular IC engine simulation software, and it is something that is being used by pretty much all the OEMs like that you can think of that makes engines. So here, let me just walk you through the setup part here. So the first thing I need to make sure is I need to select my fuel. So in this case, I'm selecting IC8H18, which is gasoline or isooctane, as my fuel species. How do you get boundary condition parameters? I'll talk about that. So for reaction mechanism, what I'm doing is I'm selecting a particular reaction mechanism, which in this case is called as the job PRF reaction mechanism file. So the mechanism file is basically telling you how the reactions are going to take place depending upon different temperatures and pressure, what is the activation energy required, what is the pre-exponential factor, and what is the temperature exponent. So if you know what the Arrhenius rate law is, these are basically the coefficients of Arrhenius rate law. If you don't know what Arrhenius rate law is, don't worry about it. It basically has to deal with how fast a chemical reaction takes place. So I basically give this reaction mechanism, and which you can download from websites of universities like UC Berkeley, MIT, KAUST University, and so on. So I'm using this particular mechanism file, and selecting this mechanism file itself is a very, very big step. If you're selecting the wrong mechanism file, if it doesn't match the fuel that you have, you're going to get it wrong. You're going to get wrong results. Then, so simulation parameters, I'm starting this just when the spray starts, and I'm running it till exhaust valve opens. I set up my time step parameters. Again, these are all CFD specific. Time step, the CFL number, which is called as the Courant number. I'm setting up my Courant numbers, and I'm setting up a bunch of other parameters that are specific to converge. So then let's talk about boundary conditions, right? So for boundary conditions, what we need to do is, for example, if you take the piston, looks like there's a question. So what is CFD? So CFD stands for computational fluid dynamics, Harshit. It's basically a technique that helps you simulate fluid flow using a computer. Does it make sense, Harshit? Neerav, which software are you using? I'm using a software called Converge CFD. Okay, so let's talk about piston and boundary conditions. So in the case of piston, we are basically saying it's a wall boundary and it's a translating wall, and the surface movement, we are saying that it's actually a moving surface. All right. Why? And we say that it follows piston motion. When I select this option, the Converge software is going to be using a slider crank mechanism in the background, and it's going to run the entire simulation automatically. Neerav, yes, is it different from star CCM? Yes, it is different. So Converge is basically, you can think of that as, star CCM was like the BlackBerry, and it was like the BlackBerry in simulation tools, and then iPhone kind of replaced it, right? So star CCM was like that. It was a very popular tool. It was being used like in all the companies, but Converge came in and they replaced pretty much everyone. Like, that's why I'm saying any OEM company, any company that makes engines is using Converge nowadays for simulating IC engines. And that is why Star CCM, right, the parent company called CD Adapco, is no longer there. It got sold to Siemens, correct? I'm not sure if you've heard of that. Okay, so that's basically it. So here we are setting up the piston motion. Looks like we have a question from Himanshu. Is the simulation possible in ANSYS Fluent? It would take you several months to do this. We basically did this entire simulation, including post-processing, in a week. If you try this simulation in ANSYS Fluent, you're going to be spending at least 3 months minimum. All right, so let's look at the liner. So the liner is also a wall. It's a stationary wall. If you look at a spark plug, it's a stationary wall. The only thing is the spark plug is at a higher temperature. So Himanshu, these type of temperature measurements are given to you by experimentalist. So basically, if you work in an OEM, right, say in GM, there's a team of engineers who do experiments, correct? They basically measure all this data and they give it to you, and that is how you set up the value. So for example, let's take a look at the exhaust valve. For the valves, what I do is I have a particular profile. I have a particular profile for the valves, which can come from multiple things. You can generate it from CAD, or you can generate it from a multi-body dynamic simulation. This is basically when the valve is going to start opening. This is the maximum lift position, and this is, for example, the valve is opening here. This is the maximum lift, and the valve is closing down here. Okay, so this profile and the starting and ending point are quite crucial. You need to give it correctly. So you kind of follow the same process for the intake as well, and that's basically a boundary condition setup. Again, I'm cutting down on a lot of details. If there's something that you want me to talk about, just let me know. So then comes your really, really complex modeling process, spray model, right? I'll just tell you what models I've used, and that will help you understand how complex it is. So for parcel distribution, I'm using something. I'm basically saying that the parcel distribution needs to be uniform, and for turbulent dispersion, I'm using the O'Rourke model. For vaporization, I'm using the Frosling model. And the evaporation source, we are basically setting a flag called 0, which says source specified species. I know that I was kind of, it might have sounded like I'm just reading the screen, but not all of these decisions have been made carefully, and I'll explain to you as much as possible. So first of all, simulating the entire spray as it is, simulating the atomization event as is impossible when you're running it with IC engine simulation. If you're doing it separately, you can, but running it within an IC engine simulation is going to be impossible, at least for the next 5 to 6 years. Why? Because atomization itself is a complex process. People have simulated atomization alone, and the amount of computing power that they have to use for that is just unbelievably crazy. You need a minimum of 200 to 300 million cells, right? That is the amount of mesh points you need to capture atomization accurately or close to accurately. All right. On top of that, if you're having combustion, turbulent flow, it's just completely impossible. So what we do is we basically say that, okay, I'm just going to approximate my spray. How do I do that? Well, let us assume that my liquid spray is made up of small drops, and these drops are called as parcels, right? So that is what you call as a parcel. And we're saying that when injection takes place, there's a cone, right? There's an injection cone, right? Because there's a spread angle. So your fuel injection will always be in a cone. And I can actually show that to you. So here, if I actually enable the injector, you can see that cone, right? That is what you call as a spray cone. That is inside that cone, injection will take place. So we are saying that we are going to be distributing parcels evenly through this cone, all right? And when the flow is turbulent, what's going to happen is your spray velocities are going to be affected by this turbulence. So you have something called your turbulence governing equations, your K and epsilon equations. They have a source term. This source term is going to basically affect your parcel velocities, and that will affect its drag force, that will affect its vaporization characteristics, everything. And here we are using something called as a Frostling model. What does this model do? Again, I'll explain it very shortly. Since I have a sphere, right, what I can do is as vaporization takes place, my sphere becomes smaller and smaller, correct? So what I can do is I can basically solve this heat transfer problem, and I can get the expression for dr by dt, which is basically saying how much the radius drops as a function of time. Because if I know dr by dt, I can compute dm by dt, right? Fairly straightforward. So dm by dt basically tells me the vaporization rate. And to capture the vaporization rate, Frostling basically proposed a formula, which is what we call as the Frostling model, right? So understanding all of these terms in this level of detail is very important so that you can use it carefully. Else you'll just be randomly selecting models, and most likely it will result in an incorrect simulation. Similarly, let's talk about collision, breakup, and drag. So if I go to here, when for example, when there's a liquid spray, it is going to atomize, it's going to break up. That breakup physics is captured or modeled using Kelvin and Mons and Rayleigh-Taylor. This is a very old mathematical model which represents the process. These constants are all very important. So you need to understand what mass constant is, what a size, velocity, and breakup time constant is. If you don't, then you can kind of trust what Converge is providing you, but there's a good chance that you will make a mistake. All right. Finally, second is combustion. So in this case, as I said, we are using that reaction mechanism. We are using something called as the detailed chemical kinetics solver. So finally, we have turbulence and spray source. Source is basically used to model the spark, right? Since we are using the spark plug here, we are basically saying that the spark, when the spark fires, it's going to inject a large amount of energy near the spark, and that is what is going to cause the combustion process to take place. And finally, you have to set up your computational mesh. So I'm using a base grid of 4 millimeters. I'm using a technique called adaptive mesh refinement. And I'm also using fixed embedding. Fixed embedding basically says, wherever I have this shading, right? So wherever I have the shading, the blue shading, I basically have a smaller mesh, right? I'm trying to resolve the mesh over there. So when you set up all of this, you need a large computer to run this. So when I ran this simulation, I was running it on a 16-core machine with 96 GB RAM. That is the amount of computing power that you need to spend. But when you do that, the results can be quite interesting. So let's take a look at the results. Himanshu, refining the mesh. Himanshu, why don't you finish typing your question? So let's take a look at the events one by one. So let's start with the intake first. And let's look at the spray simulation alone. So here what's happening is the fuel is going to come in from here. You will see that. The fuel is colored by velocity. Red is high velocity, blue is low velocity. When the spray hits the valve, the velocity becomes smaller. But then immediately when the valve comes in, the fuel is just going to get sucked in, and you can see all the turbulent and chaotic motion that's taking place. And then slowly your valve is going to close. And when the valve is going to close, some amount of fuel is going to get trapped in the intake port. And then you can see that here, your fuel has vaporized. Almost. So let's play the video one more time. So just pay attention to it one more time. So fuel is coming in. It's going to hit the valve first. And when it hits, the velocity is going to become 0, which is indicated by the blue color. And then everything is getting sucked in. Your piston is still coming down. And then you can see that slowly your parcels are disappearing, right? It's disappearing because that's your vaporization. And by the time, we basically stopped the video quite early, but let me just pause it here really quick. By the time we come here, you can see that you still have a long way to go. So for example, from here to here, we still have a long way to go for the piston. And by the time, everything will be vaporized. So this is the quality of simulations results that you can get if you do it correctly. So let's just close this guy. And here what we are looking at is we are looking at the intake event. So when the valve opens, you can see how the intake jet is being resolved, right? As the valve opens, closes, you can see that the velocity just drops, right? Initially, you can see that the velocity is very high. That's indicated by the red color. That is your maximum velocity. But as the valve opens, that velocity reduces. So this velocity jet is what is causing the turbulence to exist in your combustion chamber, and this turbulence is what helps your combustion take place successfully. Now, this entire process is happening very, very fast, but with a simulation, you can actually see it in a lot of detail, which is not possible using experiments. Okay, so finally, let's look at combustion. So for example, here we are in the process of compressing the mixture. Compression is taking place. And let me just pause. There we go. So that's your spark. And look at it. So your flame front is asymmetric, right? Just like we saw in the chemiluminescence experiment. And you're able to capture that because you're also including a turbines model. Does flow separation occur at point of max velocity? Not always, right? But in this case, near the valve, there's going to be flow separation because of the geometry. So if I continue playing this video, you have your expansion stroke, and your temperature is slowly dropping because of heat transfer and volume expansion. Okay, Harshit, I have seen engines that mixes air and fuel together while the piston goes down. Well, that is kind of what happened in this engine also. So for example, if I play the first video again, you can see that that's what's happening. So as the spray comes in, initially your valves are open, initially valves are closed. So that is why there's a lot of film formation. But then when the piston is going down, the spray is coming in, right? So that you can see that the volume is continuously increasing so that it prevents the film formation, but you still have some film, but that's fine. It's going to vaporize because you have a lot of time. You're just now starting your compression stroke. Before this, everything needs to vaporize. Does that make sense, Harshit? Okay, so what do you guys think? Are any comments regarding the simulation? The fuel is mixing before the valve is opening. Yes, that is the characteristic of a port fuel injected engine. So in fact, let me just pause the video right there. So for example, Harshit, if you see here, in a port fuel injected engine, you can see that there is a large amount of, spray parcels that are trapped inside the valve, correct? Now, this is basically very common in port fuel injected engine, and this is going to come inside the engine during the next cycle. So basically out of your injected fuel, correct? So say that you are having 100% fuel. Let us say 5% is trapped inside your port. Only 95% comes in. This is during your first cycle. But then during your second cycle, this 5% will first come in. So inside your engine, you will always have 100%, and you will always have 5% in the port. So the system kind of reaches an equilibrium at that point. Okay, perfect. All right, guys. So yeah, we're almost at 1.5 hours, which is very nice. Okay, everyone. So with that, I would like to conclude the workshop. Thank you all for attending, and I hope you learned something about IC engine simulations. Now, all the participants will be receiving a certificate, a e-verified certificate for this workshop, and this certificate will be sent to you to the registered email ID. So whatever email ID that you used to pay and register for this workshop, make sure that you check your promotions and spam folder, and you will be receiving the certificate within 2 weeks. Okay. So at this point, again, thank you so much. And at this point, what I'm going to do is I'm going to be talking about a couple of courses that we have with respect to this particular, with respect to IC engines and CFD. Before that, I think looks like someone has a question. Doesn't this accumulated fuel affect valves' metallurgical properties? Not. It might. Well, the honest answer is I don't know. And the reason why I don't know is I don't think it's a huge problem. And that's why I don't know. Because if it is such a problem, then PFI engines would not exist, right? Because the fuel as it is different. It's not like you put special fuel for a PFI engine, right? So I feel like it's not a big problem. It might cause some corrosion. It might be, but I feel like that might not happen in the lifetime of an engine. MPI engines are the same as PFI. Are you talking about MPFI engines by any chance? That is a different concept. So MPFI stands for a multi-point fuel injection system, MPFI. So that means your injector, it's an injector which has multiple points, meaning it has the injector has multiple nozzles. So in this case, if I hide my embedding, you can see that I have 4 spray cones, right? These 4 spray cones are coming from the same injector. So this is a multi-point fuel injection. So how to decide the mesh size for a simulation? That's a great question. The honest and the most effective way to determine the mesh size is grid dependency test. So, back when I was working for all these companies, right, what we do is we run the same engine with multiple mesh resolution. And there are some fundamental calculations that you can make. Meaning, in case of turbulence simulation, you're using a RANS method. You can calculate something called as a turbulent flame thickness, and your computational mesh size should be on that order. Similarly, in order for your spray models, your mesh size can be calculated approximately using simple calculations. And that is your starting point. So what you always do is you use the starting point and you keep on refining your mesh. So by CV, we might have a boom in IC engines in a decade. Is this the right time to choose this as a career? See, like I said, companies like Toyota, General Motors are putting in a lot of money in simulating or researching engines, which means if you're still thinking about choosing it as a career, getting into IC engine simulations is never bad. Because remember this, for example, in this case, if I'm able to set this up, right, I know how to set up flow. I know how to set up turbulent flows. I know how to set up combustion. I know how to, basically set up complex cases. These 3 skill sets can be used for any domain where flow is involved, which could be your gas turbines, which could be your pumps, compressors, which could be your air handling equipment device, HVAC systems, all that stuff. So Nitin, I hope I answered your question. And Basivi, I hope your question got answered as well. What is the parameter to be of interest if spray is here for grid dependence, as you mentioned? Well, what I would do is I would look at something like liquid penetration length or vapor penetration length. So the idea is quite simple. Are you familiar about liquid penetration length, Nitin? If not, just let me know. I can kind of draw a quick chart and explain. So what you can do is you can basically perform liquid penetration studies on a vaporizing spray, a non-reacting vaporizing spray, and then you can consecutively do a grid independence test to make sure that your liquid penetration length is converging. If you can do that, then you know that that is the spray, that is the grid size you need to use, and you can have that as a standard. If you want, you can. The other thing that you can do is if you have more data, what people do is they validate vapor penetration length, sorter mean diameters. You can do a lot of crazy things. It depends on the type of data that you have, but usually there has to be some type of data. It doesn't matter which CFD tool you're using, and it doesn't matter what type of simulation you're doing. You always need to kind of first do a grid dependence test, make sure that you're getting an answer before we select a particular measure solution. So in this case, the 4mm base grid that I've selected is based upon several such simulations that I've run over the past 7 to 8 years. And the thing is, if you're using a different turbulence model, things will change completely. So which grid control strategy must be adjusted for grid dependency? That's a great question. So for grid dependency, that depends upon the type of software. So it seems like you have done some type of simulation work. Can you tell me which simulation softwares you're using so that I can kind of give an answer with respect to that? Oops, sorry about that. In the meantime, I'll just answer Nirav Vyas's question. How is this flow of volume of how is the spray controlled, Nirav? I'm assuming that's your question. Well, you know the amount of fuel that you need to inject, and you typically give something called as the injection rate profile. Based upon that, you can calculate it. Nitin, if you use Converge, then I'm pretty sure you're familiar with AMR, right? Adaptive Mesh Refinement. So the AMR is a very standard parameter, and there is something called as the subgrid scale parameter, right? There's a velocity parameter and the temperature parameter. I would change that, and that will actually help you out. And if you'll see, at the end of the day, it depends on the type of engine. So if you're simulating a diesel engine, then the combustion process, as you know, is mixing control, which means getting your spray is more important than getting the combustion rate. So in that case, what you can do is, in Converge, if you're simulating a diesel engine, you would first put a fixed embedding near the spray, correct? So when you put a fixed embedding near the spray, there's a parameter called embed scale. You can adjust that for 2 or 3 different cases and see how your results are converging. And what you can do is, for adaptive mesh refinement, you can modify the SGS parameter, but you have to be a bit careful in that. But if you can do that, that would be a very consistent way of doing grid dependence test. Nirav Vyas, sir, any books or online resources to learn the software from basics? Maintaining the same base grid, yes. You can, if you have a lot of computing power, Nitin, modifying the base grid is an excellent strategy. The problem is, if you're using adaptive mesh refinement with a base grid, with a different size base grid, your seed solution is going to change. As you know, adaptive mesh refinement, before it kicks in, it takes the SGS values, which are second derivatives, from the base grid. So modifying the base grid is going to affect that SGS field that you have for AMR. So your AMR is going to be different. So there's 2 ways to do it. One is turning off AMR, which would take a hell lot of time, but then you keep on reducing the base grid, and then hopefully you get your results. But even in that, you can actually get into an issue, which is, as you know, you're using a turbulence model, right? And in this case, whenever you use a turbulence model, you have to use the right law of the wall boundary condition, which, as you know, depending upon the turbulence model, if it's a high Reynolds number model, you cannot have a very large, you cannot have a lot of mesh refinement near the wall. I'm hoping you know that. Is that something that you're familiar with, Nitin? I just want to make sure that I'm not getting too deep into the woods here. That's why. Yeah. Okay. So that is another thing. So at the end of the day, with respect to all of these things, right? It's a system that depends on a lot of factors. So here you need to make sure that your mesh refinement is correct, but it should not be too refined. One of the things that people immediately think in CFD, that if I keep on refining, my results should be super accurate. The problem with that is that's not true, especially if you're using a turbulence model. Your turbulence model has that limitation, that is, it is valid only up to a particular grid size. If you make the grid much more refined than that, your wall quantities will be wrong. So with respect to IC engines, it's not a big deal, but the way you will see that effect is it's going to increase, say, the wall heat transfer, which is going to cause a reduction in the peak pressure, like in the P theta diagram, which means work done is different, which means max temperature, emissions, all of them is going to be a bit different.